So today we're talking about solubility, and specifically what we mean here is solubility of ionic compounds in water. So this whole section is all done in water. So KNO3 is soluble in water. All right, and let me pick something that. But what if I did silver chloride? I'll show you how to use this chart in a second, but if I put silver chloride in here, let's say I had a chunk, a little grain of silver chloride, and I put it in here, all it's going to do is sink down to the bottom. GCl. It's going to stay intact. It's not going to break apart into ions. That's what we mean by insoluble. It doesn't spread out as ions into the water. Okay, that's one way to think about solubility. I think it's the most natural, intuitive way you think about it. But let me try something else. If by some means someone has dissolved KNO3 They're all floating around in the water. Here's another way to think of what soluble means. If these are floating around in water and the K and NO3 bump into each other, they're just going to bounce away. They're not going to form this. Meaning, the other way to think of solubility is the natural state of KNO3 and water is apart, not together. See what I'm saying? Maybe it'll make more sense when I do the AgCl. It is possible to have Ag and Cl ions floating around. So let's say those are floating around not from putting this in there, but from some other process. They're floating around in there, and when they bump into each other, they stick. They'll stick together, and then more and more of them will clump up together, and eventually you'll have your AgCl all clumped together at the bottom. Or usually it covers the bottom. It doesn't go to one little spot.
Are we going to have to remember which ones stay together and which ones don't?
That's this, and that I'll give you on a test. Actually, I'm going to give you the charts that are in the PowerPoint I just showed you. This is a summary of those charts. Okay, so the way to think of something that is insoluble, sure, if you put it in there, it won't dissolve, it'll just float back down to the bottom. But the other way to say it is Ag and Cl, when it's in water, its natural state is to be together. So once those ions bump into each other, they'll stick, and more will come in and stick. So I think that makes a little more intuitive sense for what we're going to describe here. Okay, so how do you use this chart? Let me grab some examples. You need to be able to figure out what's soluble and what's not for what we're doing. Here's a few. So we're back into the polyatomic ions, which is why I put that in the PowerPoint as well. So here's what you do. This side is saying soluble. Anything nitrate is soluble. This, let me give you a quick aside on this. C2H3O2. All right, that's acetate and it's structured. Am I on camera? There's the acetate polyatomic ion. You see this sometimes written as C2H3O2 negative. You also see it sometimes written as CH3, this part, COO. It's the same molecule, it's still acetate. Those are just different ways to represent it in a formula. You might even see CH3CO2 negative for those two. So don't get lost. Our book, I think, does this. That other diagram I got out of another book does, I think it does this. But anyway, that one's just a weird one. That's acetate. So the point is, anything that has nitrate in it is soluble. It doesn't have any exceptions. Anything that has acetate in it is always soluble. It doesn't have any exceptions. This one is saying, for instance, chloride, AgCl Hg2, it's called mercuric. It's 2 mercury. It's a fairly common ion. Hg2Cl2. Maybe we do it like this, AgCl, because there's 2 of them, HgCl, and then Pb. What I'm saying is, anything with chlorine in it is soluble, except in these cases. So these are negative, these are positive. When the positive ion is one of these for Cl, it is not soluble. It's an exception to being soluble. See what I'm saying? And same with the others. Br, R2. It's exceptions for all of those. So that's how you read this top chart. For sulfate, SO4 is sulfate. Silver sulfate, strontium sulfate, barium sulfate, lead sulfate, calcium sulfate are all insoluble. And then anything else besides those is soluble. That's how you read this chart. All right, you're kind of doing it the opposite way down here. Anything with sulfur, 2 negative, is insoluble unless it's NH4, that's ammonium. I wrote first column here. Books like to tell you that these are called the alkali metals, and these are the alkaline earth metals. So I think that chart calls, instead of saying first column for all these, it says alkali metals, but I just called it first column. So all of these are exceptions for all of these, the whole row. And in these cases, plus a few more. Those 3 more are right here. So they're in the second column, CaSrBa. So that's those. So the point is, it. The point is, NH4, there would have to be 2 of them because it's plus S. If I ask you whether or not that's soluble, you look around in here and you find the S and you go, okay, anything with S is insoluble except for these. These are soluble, so that one would be soluble. Soluble. You follow that? Okay, so try it. K2SO4, is it soluble or not?
No.
Oh, For those of you on camera, I've got a little periodic table sketched over here, but anything in the first row, the first column of the periodic table is an exception. K is in that first column, so it's an exception. So this is soluble. Because it's insoluble if there are no exceptions. And so, where was I? Sulfate. I was looking at the wrong one. Sulfate. Okay. Everything sulfate is soluble except for these. And that's not one of the exceptions, so it's still soluble. It's just by different logic. You follow that? Is this soluble, K2CO3? So it's insoluble unless it's this or something from the first column. K is from the first column, so it's soluble. You with me? Down here, the exceptions are soluble. Up here, the exceptions are insoluble. AgI. So here's I. All iodines are soluble except these. Ag is one of the exceptions, so this is insoluble.
Can you explain the second one again?
This one?
Yeah.
Did I do it wrong? CO3, everything with CO3 in it is insoluble except these. First column, K is in the first column. So this CO3 is not insoluble, it is soluble because the K is from the first column. Down here, the exceptions are soluble.
Okay, so like all the exceptions, you can just write like first column with all of those.
Say again?
Like the first column is an exception for both, like everything.
No, it's only, it happens to be, show up in all four of these spots. It's not anywhere up there. So the first column goes with this first column goes with this, first column with this.
Okay.
So all of these down here have NH4 and first column as their exceptions.
Okay.
It just so happens all of them do.
Okay.
These have a few more exceptions. Ca, SRBA, that's these three in the second column. All right, where am I? CO, CO3, that's cobalt, CO. There's CO3, all CO3s are insoluble except for these. Cobalt is not in the first column, that's a transition metal right in the fat part of the periodic table. So this one is insoluble. This has I in it, so you look at I here. Everything with I in it is soluble except for these, and lead is one of the exceptions, so it's insoluble. The nitrates and acetates are easy. If you see nitrate, it's soluble because there are no exceptions to that one. Anything nitrate is soluble. I guess I like CO3 because I picked it up several times. CO3, everything CO3 is insoluble except for these. Nickel is not in the exceptions, so it's soluble. Sorry, insoluble. Cobalt with either of these is soluble. This is cobalt, not with one of those, so it's insoluble. Chromium phosphate. Everything PO4 is insoluble except for when it's with NH4 or something for the first column. Chromium is a transition metal. It's not in the first column and it's not NH4, so it's insoluble. I like my little summary over there. I think it's easier to read than either of those charts, but it's these charts that I'll give you for the test. This is the one from our book that I just thought was confusing. They've got OH, they've got this and this together because they have the same exceptions. I don't know why that confused me. CO2 and PO4, yep, those are the same too. So that's the reason they did it like that. deal with, no. Some of these are slightly soluble, but that doesn't end up causing a problem. Meaning partially dissolves and partially doesn't. And I think this is just a straight up repeat of everything on the other chart. It's just a chart from a different book. All right. Having told you that, how to decide what's soluble and what's not. Let me write this for you. I don't have questions up for these yet, so your practice is going to be, any practice you might want to do is exercises are one more thing to tell you about ions. If you've got all those ions floating around in water, it's because it's positive and negative. If you try to run a current across this, a current will run. Because there's a negative side and a positive side. Let's say that's the positive side and that's the negative side. Positive ions can be attracted here, negative ions can be attracted there, and a current can flow through the water. And it's called an electrolyte. It is the same thing that you hear about when you want to hydrate, you need to get a lot of electrolytes. Your nervous system basically runs off ions to send nerve signals. So you got to have lots of ions. So that's why everyone says get your electrolytes when you're exercising or whatever. But if it's something that doesn't dissolve, there's water, and you put electrodes in it. There are no ions. What was an example? If you put AgCl in there, it's just going to float down to the bottom. There are no ions. Therefore, electricity won't flow. That's a non-electrolyte. Non-electrolyte. In some sense, this is telling you what solutions will be an electrolyte and which ones will not. Is that simple? In 47 and 48, say, which of these will be an electrolyte? Or the phrasing might be, which of these will conduct electricity? It's the same idea. Things that dissolve will, so those are electrolytes. Things that do not dissolve will not be electrolytes. 49 and 50 just ask you straight up, which one of these dissolves? But electrolytes are dissolved, non-electrolytes are not dissolved. There's that. And just remember, everything we're talking about here is ionic compounds in water. Before I go on, let me... Precipitation reactions. And some exercises to look at. I will get questions on D2L for this. '53 and '54. That's these that I put in the PowerPoint. Because it just says potassium, it literally says in words, potassium carbonate and lead 2 nitrate. And since I don't want you going back to the naming schemes for this test, because I've already tested you on that, I went ahead and wrote those out so you can use them as practice. And we will very likely get to 8.6. I'm just going to say net. equations. 55 and 56. So that's what to look at if you want to practice what we're doing today. I might get to acid-base too. Okay, precipitation reactions. We've talked about reactions some. Like you've seen something like this. 2Ki plus PbNO3, 2. Those react and become Pb. You're going to have to do a little bit of balancing here, but I'll show you what I mean. So you've seen stuff like this before. This was a particular subtype of reaction called precipitation reactions. The first thing you want to do is decide, actually let me push this forward and do this. You're likely to get it like this. So it's a question mark. What do we create here? You can fill in that other side by going, this is the positive, this is the positive, these are the negative ions. What you're going to do is just swap them. I'm going to take this positive ion and put it with this negative ion. I'm going to take this positive ion and put it with that negative ion. So now I'm going to have KNO3. If I split this out into ions, I would have K plus and I minus. You can tell that straight off the periodic table. You can look at the polyatomic ions and see, look up NO3 and you'll see that it's 1 negative. So what's the charge on lead? On Pb? You've got 2 of them. So that means Pb 2 plus. So you infer that charge. So what I'm going to do over here is I'm going to put the K and the NO3 together. K is plus and NO3 is minus, so I can look at K, NO3. But notice there's 2 Ks. The 2 Ki means literally there's a Ki and another Ki. That means there's a total of 2 Ks. So I have to put a 2 here. And I have 2 NO3s. So the 2 KNO3 means I have K and NO3, K and NO3. I'll just write them together. That 2 literally means there's 2 of those. 2 Ks, 2 Ks. There's also 2 Is. And there's 2 NO3s. How do I do this? There's 2 of those, and then there's 2 NO3s. That's what's actually over here. So K and NO3, 2 of those, 2 of those. All right, now I'm going to put the PB and the I together. PB is 2 plus. I is 1 minus, so I need to do that. So there's my 2 I's and 1 PB. It's balanced now. So you might need to do a little balancing when you do this. But notice what I did is swap the ions. Positive ion with this negative ion, positive ion with this negative ion. Those are going to be the products. So you can predict the products just by looking at what the reactants are made of. With me. Next thing I want to do, starting with the reactants, I want to know if they're soluble or not. Is Ki soluble? There's I. And it's soluble unless this, and this. So is it soluble? If it's soluble, we do this. AQ in parentheses. That literally tells you that you don't really have Ki. You have K plus and I minus floating around in water. The AQ means aqueous, literally referring to water. It's literally saying this is dissolved in water. AQ. All right, what about PbNO3? Is that soluble? Everything in O3 is always soluble. So I'm going to put an AQ here. A reaction will not occur if both of these don't dissolve. If only one of them dissolves, you'll have ions floating around and then a chunk down at the bottom. And if it doesn't separate out into ions, then the ions can't exchange and form this. So at bare minimum, we need both of those to be aqueous. Okay.
Wait, sorry, can you explain that again? Sorry.
If I put Ki in water, I get that. And let's say instead of PbNO3, let's say I put PbCl2 in water. Cl, Pb is an exception. That's not soluble. It's not going to do this. That's not going to come apart like that in water. It's going to stay together. And we need the ions to come apart so we can rearrange them
So you
to get
want
these.
both of those to be,
Yes. Both of these need to be soluble for this reaction to even occur. So you check that first. Make sure they're both soluble, and they are. KNO3, is that soluble? It is. All NO3s are soluble. Lead iodide, is that soluble? Lead 2 iodide? It is not. It's one of the exceptions here. What we put for that one is S for solid. S means solid, AQ means aqueous. Don't get confused and think that means soluble. This is the opposite of soluble. It stays a solid in the reaction vessel. Now, let me reiterate this. We've got this floating around. We've got some of that floating around. All floating around in the water. We also have some Pb2+, and what else? Some NO3 floating around. All of that's floating around in the water now because that came apart in ions and that came apart as ions. If a K and an I bounce into each other, by the way, if you've got a beaker of water and these ions are in it, even if you just had a beaker of water, the water is moving. It just doesn't look like it is to you, but the water molecules are constantly floating and moving around. So will the ions if they're down in there. So these are moving around. A K and an I meet each other. And this was that second definition of solubility that I gave you. Their natural state in water is to be apart, so they'll just bounce away from each other because Ki is soluble. Natural state of Ki in water is to be apart. If Pb and NO3 bump into each other, they're just going to bounce apart again because their natural state in water is to be dissolved. If K bumps into NO3 in water, they'll just bump into each other and bounce away because both of those, their natural, KNO3's natural state in water is to be apart in ions. But as soon as a Pb and an I bump into each other, they stick. They stick to each other because their natural state in water is to be together. You follow that? And they'll just keep building it up. It is PbI2, so it'll collect another I, and then it'll collect more I and Pb, and it'll make one of those crystal lattices. It'll just keep building up until it becomes a chunk, and then it'll float down to the bottom. So Pb and I, those ions come together, they form the solid. This solid that falls down to the bottom of the beaker, that's what we call a precipitate, hence the name precipitation range. It's the same thing they mean when a meteorologist says we're going to have precipitation tomorrow. That means water falling. It's the same idea, except it's a solid. It falls down to the bottom, precipitate. Things to watch out for. What if I change this to what if it was Ca, which is 2+, so I can still use this? we've checked everything, and we found out that's soluble, that's soluble, that's soluble. Is calcium iodide soluble? There's iodide. Everything iodide is soluble except for these. Calcium is not in the exceptions, so it is soluble. The problem we have here is all that happens is we get Ki plus and I minus, lots of them, K plus, I minus, K plus, I minus, floating around. And we also have calcium 2 plus, NO3 minus. All those are floating around, and every one of them, if they bump into each other, they're going to come apart. So you never form a precipitate. You never get anything for the reaction. If you have this case, what you say is, in that case, we say no reaction. You just end up with a beaker full of ions, and you never get a solid that you can filter out and separate. See what I'm saying? So if everything's soluble, it's no reaction. If only one of these is soluble, it's still no reaction. You have to have, at bare minimum, you need two things that are soluble, and then over here, one soluble and one not. Then it's a precipitation reaction. You have to get a precipitate. In our case before, it was PB. And you have to have these two, both of these things dissolve. Otherwise, you're not going to get a product. You're not going to get a solid form on the other hand. So no reaction is when everything is soluble. You also get no reaction. Here, let me, that's a reaction. A reaction occurs there. If you have dissolves in water but does not, or does not dissolve and does, no reaction, because if you got two things that dissolve, you can have a reaction. If both of these don't dissolve, then the ions can't change places and form something new. Same here, if this doesn't dissolve, the ions can't change place and make something new. And I suppose I could say, if you got two solids and neither of them dissolve, you get no reaction. And I guess the only thing left off is, what if both of these dissolve, but both of these are naturally ions in water? You get no reaction there either. So the only way you can get a precipitation reaction is if both of these are soluble, and one of these is soluble and one of them isn't. I think it's probably true that if both of these are insoluble, I suppose you could still say you had a reaction, but you can't just filter it and separate because they're all together in there. So really, this is the case you're looking for a reaction. One of them is soluble, one of them isn't. The one that isn't soluble is the precipitate. And that precipitate is generally the point of doing the reaction in the first place. You filter it out, all the ions go through the filter with the water, you catch your solid on the filter paper, you can dry it out, save it, use it for something else another day. The point of precipitation reactions is to get that precipitate. Okay, precipitation reactions. Go to, I guess I didn't. 51, 52, 53, 54. Just want to see how those are phrased. Okay, complete and balanced each reaction. If no reaction occurs, write no reaction. Strontium over there. One of these charts has strontium and I think calcium 2+. Those are the ones that are partially soluble, so I'll add those there. All right, I'll do 52D. Okay, what you're given for these is the reactants. That's NH4 plus ammonium Cl minus.